myself Dr. Priti Jagwani from Department of Computer Science, Arabic College, University of Delhi. So in my previous lecture we looked upon learning agents, and we have also seen the three representations of our states of agents or different states. So one was atomic, another one was factored, and the third one was the structured representation. With the completion of that module, today's agenda is the problem solving agents. So problem solving agents, when we talk about, let us see first of all what is problem, what is the problem formulation, and then how are we going to kind of solve these problems with the help of various agents, or how are we going to formulate the problem. This is the first thing which we are going to look into in this lecture. So problem formulation, when we talk about, it is actually the process of deciding what actions and states to consider in order to achieve a particular goal. An agent with several immediate options of unknown values can decide what to do by first examining the future actions that eventually lead to states of known value. So that means the first is we need to, or your agent actually needs to look for a sequence of actions which is going to help it to reach to a goal. And this process of looking for a sequence of action that reaches to a goal or that takes an agent to a goal is called search. So that means out of various available possibilities, your agent is needed to search that which particular possibility or which particular path or which particular sequence of actions I should take on, so that I will be able to reach the goal. So a search algorithm, if we talk about, that takes a problem as the input and returns a solution in the form of action sequences. Once a solution is found, the action your agent has recommended can be carried out, and this is what we call the execution phase. So first of all, there is a search phase, and then the execution phase comes out when the solution is already kind of already found out, and the actions which are being recommended, now your agent is ready to carry out those actions. After formulating a goal and a problem to solve, your agent calls a search procedure to solve it, or that problem solution is being executed. It then uses the solution to guide its action, doing whatever the solution recommends as the next things to do. So for example, from A you need to go to B in case of a root finding problem. From point A you need to go to B, and then from point B you need to go to point E. So this is what actually giving a solution, or giving a solution in terms of its action line, doing whatever the solution recommends as the next thing to do. So from moving A to B and then from B to E. Typically the first action of the sequence and then removing the step from the sequence. So from A we have kind of reached to B, so then that A has to be removed from the sequence. Once the solution has been executed in this manner, the agent will formulate a new goal, we can say. While the agent is executing the solution sequence, it ignores its percepts when choosing an action because it knows in advance what they will be. So that means in this kind of situation, your agent need not to look into the current percept, because the line of action has already been kind of determined by the search procedures. But before this whole kind of solution execution, your problem has to be defined in a particular or in a structured formal way, that okay, this is the state from where I want to start, this is my goal, all these actions can be taken, these are the actions which cannot be taken, and so on and so forth. So a well defined problem has to be there, along with kind of, we can say we need to find the solutions. Yes, a problem can be defined formally by 5 components. Now let us see what are these 5 components, and then we try to understand about these components, and then definitely we are going to take upon various examples. So, the 5 components through which a problem can be defined in a structured way is the initial state, then there comes the next one, which is actions, third is the transition model, then we have goal test and goal state obviously, and we have path cost also. So, I repeat: initial state, actions, transition model, goal test and path cost. Let us see all these components one by one. So, initial state, the most simplest one, we can say the initial state that the agent is starting in is your initial state. Now, if we talk about the next component, which is the actions. So, actions is actually we can say, given a particular state, let us say S, the actions which are to be done on that state S, actions S, that component returns the set of actions that can be executed, and each of these actions, if it is more than one actions, those actions are applicable in S. Now, let me give you an example here. So, in case of a root finding problem, let us say there is an state A in which your current state, in which your the agent is currently in. A is my initial state. So, from A there are 3 paths, one is going to B, another one is going to C and third one is going to D. These are the 3 paths. So, actions of A, actions AS or actions here in case is A, which is the point, returns the set of actions which is move to B, move to C and then move to D. So, basically it is a description of the possible actions available to the agent at that particular time. Now, there is no possibility of agent moving to the point F, because there is no such path from A to no direct path from A to F. So, only the direct path which are available are from A to B, A to C and A to D. So, when we say actions A, that are going to return the set of actions that can be executed, and each of these actions is applicable in that state S. So, only the applicable states here in the example of route planning which I am talking about are only move to B, move to C or move to D. So, for example, from the state in A, that means your agent is presently at A, the applicable actions are go to B, go to C and go to D. So, it is not only the actions, along with it we also need to look into the applicable actions. So, 2 components of this problem formulation we have seen, one is the initial state and another one is the actions, and within the actions we have seen what all are the applicable actions. Moving further with the next kind of moving further, there is the transition model, but before going into your transition model we need to understand one component which is about a function and that function is known as result, and it is having 2 components, one is the state and another one is the action. So, let us see a description of what each action does. That means the formal name which we are going to give to this thing is actually a transition model, and this transition model is specified by the function result S comma A, where S is a state and A is the action. So, this result S comma A is going to return the state that results from doing action A in the state S. So, for example, your agent is at point A presently, and now the action which is go to B or go to C or go to D, any 3 of these, any one of these 3 is going to be operated upon. So, result A, which is the state comma your go B is going to be in B. So, now after this movement or result of this transition is going to be that your agent will now be in the state B, because it has moved or it has kind of went from A to B. So, we also use the term successor to refer to any state which is reachable from a given state by a single action. So, for example, which I was just talking about, result of in A, which is the state, comma go B, which is the movement, is going to be in B. So, now your actual learning agent is in the state B, and here B is also a successor of A, because it is the state which is reachable from A by a single action. So, initial state, then the actions and the transition model. Together these three components, initial state, actions and the transition model, implicitly defines the state space of the problem. Now, what is the state space of the problem? State space says it is actually the set of all states which are reachable from initial state, not directly, not in a single move, but by any sequence of actions. So, let us say there are points starting from B to let us say kind of Z or K, let us say. So, every state which is B, C, D, E, F, G till K is actually in your state space, because it is the state, if it is obviously reachable, it is the state which is reachable from the initial state A by any sequence of actions. So, that is a possibility that from A we are going to B, and then from B we are going to E, and then from E we are going to F. So, all the states which is B, then E, then F, because F and E are actually reachable from A, so is B, by any sequence of actions, and set of all such states is actually known as state space of the problem. The state space is actually we can say depicted in the form of a network or graph, in which the states are being shown as the nodes, and the link between these nodes or link between these actions are nodes are actually the actions. Now, moving on to the next one, which is the goal test. The goal test determines whether the given state is a goal state or not. So, for example, in the route finding problem, we need to find a route starting from A to K, and let us say presently we are at state F. So, that this F is not actually a goal state, because we want the goal state is K. So, the goal test is something that determines, or it is kind of an evaluation that determines that whether this given state, here F in this example, is actually a goal state. So, here it says no, because the goal state which we are looking for, or the destination state, is actually K, not the F. Now, sometimes it is possible to have an explicit set of possible goal states. So, kind of for example, route planning I was talking about. So, goal states are, let us say, fixed, and the goal test simply checks whether the given state is one of them, yes or no. So, but there is an explicit set of possible goal states. So, for example, in our tic-tac-toe game, what is the goal state? So, kind of a we can say straight line or maybe diagonal of one particular symbol is actually a goal state. Now, that can be a horizontal line, that can be a vertical line, that can be a diagonal. So, explicit set of possible goal states is there. But let us say if we talk about chess. So, chess is something we can say it is not having explicit goal state, because every time there is a situation, or every time it is a checkmate situation, the goal is actually to reach a state called checkmate, where the opponent's king is under the attack and cannot escape. So, in chess the goal is to reach the checkmate situation, and it is kind of a specified an abstract property to be specified, rather than explicitly enumerated set of states. So, we actually it is practically impossible to say okay, these much of kind of states we can say are going to be the goal states in case of chess game, because there can be so many kind of lacks of the possibilities where of the lacks of the possibilities of the pieces arrangement of the chess game, and state checkmate is actually an abstract property. rather than being an explicitly enumerated set. So, in chess we do not have such a set, so that we can say okay, these are the 10 states and any one of them can be a goal state. No, it is kind of an any checkmate situation can be a goal state. So, that is why I was saying sometimes it is fine that we have an explicit set of possible goal states, but other time there can be an abstract property which is going to define your goal state, as we have seen in the example of checkmate. Also, a path in the state space we can say is a sequence of states which is connected by a sequence of actions, and this is related to your representation of states with the help of that graph and all that. Moving further, we have seen goal test, we have seen goal state also. The last component of your problem formulation of well defined problem, it is the path cost. The path cost is actually a function that assigns a numeric cost to each path. So, from going from A to B, it is a 10 kilometer path. So, the cost function is going to give you 10 kilometers. And why do we need this path cost? Because your problem solving agent chooses a cost function that reflects its own performance measure, or we can say it is going to choose the best cost function. So, for the agent trying to get to a particular city, time if it is of essence, so the cost of the path might be its length in the kilometer. So, shorter the length, kind of lesser the time is. Similarly, we have a step cost. The step cost of taking an action A in the state S to reach a state S dash is denoted by C S A S dash. So, this is what your step cost is. Also, we can say a solution to a problem in an action sequence, which is action sequence is starting from your agent is taking up, your agent is starting from the initial state and going to a goal state. Solution quality is also to be measured by the path cost function, and an optimal solution which has the lowest path cost, maybe least number of kilometers traveled, or it could be the least amount of time given on the path. So, the lowest path cost among all the solutions. Now, this problem solving approach in which we are going to define a problem in a well structured way using these 5 components which we have just studied. The problem solving approach has been applied to a vast array of task environments. Now, these task environments can be kind of some toy problems which we study just for the purpose of kind of exploration and learning, or it could be some real world problems which are not illustrative of any kind of toy situation, but they are actually the applications of the real world. When we talk about any toy problem is intended to illustrate or exercise various problem solving methods. It can be given a concise or exact description, and hence it is usable for the purpose of learning or for the purpose of research, and it is also usable to compare the performance of various algorithms. While if we talk about your real world problem, so toy problem is the problem which are kind of indicative of the research, or which are mostly used in comparing the performance of algorithm for research or learning purposes. While if we talk about the real world problem, that is the one whose solutions people actually care about. Now, such problems tend not to have a single agreed upon descriptions, but we can give kind of a general flavor or general taste of their formulation. So, for example, if we talk about the toy problem, so your vacuum cleaning world, which example we have described couple of times in my previous lectures, that is actually a toy problem. While if we talk about kind of a route finding problem, that could be a real world problem where people are actually worry about, they do worry about the solution, while if we talk about this 8 tile puzzle, or it could be your vacuum world, these are the toy problems where user actually, or the people in the real world, they don't care about these solutions. Now for example, if we want to represent that toy problem which is of vacuum world using the 5 components which we have just seen. So let us see what all states are possible, then what all actions, transition model, then goal test, path cost, and so on and so forth. So let us consider that vacuum world problem again. Let me help you recall that there were only two kind of states or two situations, we can say. That was the whole environment A and B, and there is a vacuum cleaner agent as it is kind of shown in the figure, and these two corners or these two areas which are A and B can have dirt into them. So now let us say your vacuum cleaning agent is placed in the location A and it takes a left, which is the action, which is a denoted action. So denoted actions consist of L, which is for left, R, which is for right, and S, which is for suck. So if it takes L's, it is going to be in the similar situation. If it takes R, it will transit to the B corner. At the B corner, if it is going to take R, it will be in the same corner, and in the B corner, if it is going to take an action of L, it will come back to A, we can say, and this is what is actually being shown here. Now from a state where the vacuum cleaner is in the corner A and the A is actually dirty and it is taking or it is opting for the action suck, then your A will be clean, but B is still dirty. Then from here it can also move on to L, it will be in the same situation. R, it will move to the B. From B it can take L and come back. But in B, if it kind of takes the action suck, then here B is now we can say is clean. But initially, if so, here in this graph which is shown on the screen, you can say what is the action it is going to be taken, it is going to take. One is left, another one is right, and third one is S, which is for suck. Now what is going to be the effect of that action on the environment is being shown here with the help of figures, and these figures I can say are actually kind of self-explanatory. Now let us see the states. A state is actually determined by two things, the agent's location and the location of the dirt. The agent is in one of the two locations, one of which or both might contain the dirt or might not contain the dirt. There are 8 possible situations, because for every two situations there are different possibilities. So 2 into 2 to the power n, which is nothing but 2 to the power 2, because here it is only 2 possibilities. So 8 possible situations, and a large environment with n locations has n into 2 to the power n states. So this was about the states when we were talking about the vacuum world. Initial state, any state can be designated as the initial state as we have shown in the figure. Actions we talk about left, right and suck, just 3 actions. Larger environment might also include up and down, but here as we are considering the only 2 corners, so we are just moving left and right. Transition model, if we talk about, the actions have their expected effects, except that the moving left in the leftmost square not going to affect, moving right in the rightmost square is not going to affect, and sucking in a clean square have no effect. But except these situations, the actions have their expected effect. Now if we talk about the next component, which is goal test. So goal test says, so this goal test here is going to check whether all these squares are clean or not. So this is the goal, is to make the environment or the world clean. What is going to be the path cost here? So, let us assume that each step is going to cost 1 unit. So, the path cost is actually the number of steps in the path. So, we have seen here the toy problem, which was vacuum world. We have seen what all possible states are there, what can be the initial state, what all actions are possible, what all actions are going to affect, then what is going to be the transition model. Apart from that, apart from this, we have also seen the goal test and the path cost. Now, here in this lecture, we talk about the different, for well structured problem formulation, and that well structured problem formulation we have seen with the help of 5 components: initial state, actions, transition model, goal test and path cost. We have also seen the distinction between the toy problems and the real world problems, and apart from this we also learnt about the problem solving agents, and this problem solving component we have seen in detail with the help of its 5 components and one toy example. More example are going to be covered, whether these are the some toy examples, also some of the real world examples, but because of the paucity of time I am stopping here. I will be taking this topic with some more examples in my next lecture. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.